In the Newtonian gravity-naive space-time, where we have just worldline curvature and ordinary flat, space-time, whatever, I'll represent it as this. There's no real quantity like that. There's no such thing. But this is the shadow of this. This exists in differential geometry. This is the shadow of this thing. This is exactly the worldline curvature. This is the acceleration. It's just a symbol. It's not like the RT component of something. This is definitely the RTT component of something. This is just a symbol to show you kind of like an intermediate level. All right? What is this really in our space-time theory?
Worldline curvature.
Worldline curvature. The curvature of the straightest lines in this curved spacetime, which we expect to be similar functionally to the curvature of these world lines, right? Not the acceleration, not the worldline curvature, but the curvature of the straightest lines in this curved spacetime. We might expect maybe that in the Newtonian regime, where Newtonian physics is correct, since the equations give the same result, but we can write A also as a connection coefficient. Why? Why do I say that A is a connection coefficient? How did we start our mapping? What are we looking for? What are we looking to map? We know that the gravitational acceleration is the flat space-time worldline curvature, and that is somehow a shadow of something that exists really in curved space-time. What is it a shadow of? What curved space-time quantity is it a shadow of? Okay? We have a geodesic equation. The geodesic equation has the second derivative of, let's say, r with respect to a parameter, which we're going to be able to choose as time, as we said. And that's going to be equal to a whole bunch of things depending on connection coefficients, which define the geodesic for a warped spacetime. We expect that that whole equation is going to boil down to this r double dot is equal to gm over r squared. Okay? So this gm over r squared is clearly a shadow of something to do with the connection coefficients in the curved spacetime theory. All right? We know that in the flat space-time picture, it's a worldline curvature. That's simple. It's just calculus. We know that this worldline curvature, though, is actually a shadow of something, right? The worldline is curved or uncurved because really it's a geodesic. And in the geodesic, you have connection coefficients, which are going to boil down to this gm over r squared, this curvature. Okay? So we can write, if the connection components are these gammas, we're going to write the shadow also, just as a simple, we're going to write it as a gamma. But instead of having 3 indices, we're going to write it with 2. Okay? This is my own notation. It's not standard notation. It's just a symbol. So when I write this, okay, you'll see the equation, the first equation on the left-hand side on the top. You have this gamma with an r and a t. All right? It's not a geometrical object that's well-defined. It's the shadow of a similar quantity, a gamma, in a curved spacetime. Okay? Which will be also intermixing the r and the t. All right? We're going to have a geodesic equation in a curved spacetime. The geodesic equation is going to have r double dot equals a bunch of gammas. Okay, that's the geodesic equation. That's going to somehow reduce down to r double dot equals gm over r squared. Correct? Right, that's our theory. We know that the acceleration equals gm over r squared. That's simply the curvature of the worldline in flat spacetime, nothing exotic. Okay, purely Newtonian flat spacetime, whatever that means. Right? That worldline curvature will be something more complicated is reduced to. The geodesic equation with all the gammas will reduce to this worldline curvature. Okay, so I'm calling the object that it reduces to this gamma with gamma RT with two indices. It's simply the worldline curvature. Okay? It's a worldline curvature, but we know that the worldline curvature is a shadow of something that's happening in curved spacetime. And the thing that's happening in curved spacetime are these gammas in the geodesic equation. Right? Have you all seen the geodesic equation? So you know what I'm talking about, right? You have the second derivative equals to a gamma times... is there somebody who hasn't seen it? I'll just show it to you on one of the papers, or show it right on the board. So, everybody seen it? Okay. So again, we have this geodesic equation with gammas. We know that that gamma is going to show up in this flat spacetime as the curvature of the worldline. So I'm just labeling the curvature of the worldline since there's no symbol for it. I'm going to call it a gamma, but instead of with 3 indices, I'm going to call it gamma with 2 indices. So it's not the same as the gamma, it's just the shadow of all these gammas in flat spacetime. So we have the divergence of A is equal to rho. The divergence part of the equation I can write as derivative plus gamma r theta theta, gamma, right, times A. That's simply the ordinary divergence for curvilinear coordinates. And I'm operating on A, but A I know is a worldline curvature, so I'm labeling it as gamma RT because I know that it's a shadow of something that has to do with gammas in the geodesic equation of the curved spacetime. Okay?